Okay, hello everyone. Good morning, all of you. So we start with our quote today. Character cannot be developed in ease and quiet. Only through experience of trial and suffering can the soul be strengthened, vision cleared, ambition inspired, and success achieved. So only when you face the more number of trials and sufferings, the more you will be strong, your vision will be clear, your ambition will be inspired, and success will be achieved. And today is the birthday of Ray Dolby. I think you heard this name many times when you see movies and all. Dolby is Dolby sound.
Audio.
They say Dolby sound, right?
Yes, sir.
Yes. Okay. So he is American physicist, engineer, and inventor of the Dolby noise reduction systems. Dolby is famous for innovations ranging from the high-quality cassettes we use in our car stereos to the latest digital surround sound in movie theaters. As a high school student, he went to work part-time for Ampex Corporation. While still in college, he joined the small team of Ampex engineers dedicated to inventing the world's first practical video tape recorder, the Ampex VTR. Dolby founded his own company, Dolby Laboratories, in 1965. His first development was Dolby A-type noise reduction, air audio compression, and audio compression and expansion, which dramatically reduced background bias, background hiss in professional tape recording with no discernible side effects. Okay, so he is the great inventor, and because of him, we have beautiful sounding in theaters and all. And he says, to be an inventor, you have to be willing to live with a sense of uncertainty, to work in this darkness and grope towards an answer, to put up with anxiety about whether there is an answer. Okay, so such zeal and struggle will be there in any inventor. Okay, we have completed all the governing equations, generalized, a little bit generalized, and the continuity equation, momentum equation, and the energy equation. And all of them together, we can write them in non-conservative conservation form and also in matrix form, in generic form, like that. So just we will see the equations again. So the summary of equations in conservation form, right? So here time. So we will have in the equation conservation equations. These are also called transport equations. So we will have unsteady term, convection term on the left hand side, and diffusion term and source terms on the right hand side. Okay, so in general, so unsteady term and convection term, so which related to inertia and all, and diffusion related to viscosity, and source terms related to pressure and gravity. Okay, so that is the way normally we'll have. Okay, so these are the equations. And so momentum equation with primitive variables in conservation form. So here I don't have all primitive variables here, stresses are there. So stresses are, if substituted in terms of velocity gradients, then I will have all primitive variables in this equation. And then energy equation in non-conservation form. If on the whether it is conservation or non-conservation just depends on the left-hand side of the equation. If I have total derivative, it is non-conservation form. If I have unsteady term and convective term, then I will have conservation form. The right-hand side will not be different. Okay. And so energy equation in conservation form. So you can see here the unsteady term and convection term. But in non-conservation form, I will have total derivative here. The remaining things will be as it is. And so an internal energy equation in a non-conservation form. So here rho dE by dt, so it is non-conservation. And if you see all the terms here, so this is the equation. And again, these are stresses are there. If stresses are substituted in velocity gradients, then I will have this equation. So mainly, if you see the total energy equation, if I see the body forces, in the total energy equation, I will have rho B dot B, rho UBX plus rho VBY plus rho WBZ. But if it is internal energy equation, no body force. And the enthalpy equation also. There is no body force term. It gets cancelled. But when you come to pressure term, if you see the total energy equation, I will have okay, so this will be there on the right hand side. Okay, so that is dou of pu by dou x plus dou of pv by dou y plus dou of pw by dou z. This will be there. If I have internal energy equation, so I will have p del dot v on the right hand side, that is p into dou u by dou x plus dou v by dou y plus dou w by. If it is enthalpy equation, I will have dp by dt. Total derivative of pressure will be there. Okay, so that is the difference between the equations just I wanted to tell. The remaining things will be almost as it is on the right hand side. Okay, so this is the, so you don't see any pressure force, and this viscous term in internal energy equation and enthalpy equation is called as dissipation, represented by phi. So this particular term, right, mu into 2 into dou u by dou x whole square plus 2 dou u by dou y whole square, all these things, this particular term is called as the dissipation. So again, this in internal energy equation in conservation form, that is unsteady term and convective term. So with primitive variables, again the same thing. Okay, some comments we see here. One is all are coupled, non-linear, simultaneous, partial differential equations. And the problems differ in boundary conditions and the flow domain. This is where the variation comes from equation to equation. And the other points are, yeah, the conservation form of the equations. In the conservation form, equations, so you will have something like dou of rho v by dou t plus del dot rho v, sorry, dou rho by dou t plus del dot rho v equal to 0, or dou of rho v by dou t plus del dot rho VV is equal to, similarly, dou of rho ET by rho T plus del dot rho ETV is equal to. So here the convection term is in divergence form. So these are called also as divergence form of equations. Right. They're called divergence form. And number of variables are 7, rho, P, U, V, W, E, T. So if E also is taken to be a variable because I am getting internal energy, uh, in total energy, E plus V square. So E I am getting. So I should have another equation related to E and T. So that is called as caloric equation of state, or E equal to CVT. Okay, P is equal to rho RT. So one continuity, 3 momentum, 1 energy equation, 5, and P equal to rho RT gas equation, and this E equal to CVT also is to be there because E is there. And so as I told, in fluid mechanics, we refer to momentum equations as Navier-Stokes equations, but whereas in CFD, the whole set of equations are referred to as Navier-Stokes equations. And this also I told, implicit Navier-Stokes equations are referred to as Euler equations, and the solvers are Euler solvers. And the equations for generalized situations and each individual problem is identified by flow domain and boundary conditions. Okay, so this we have expressed them in matrix form or generic form or strong conservation form. So this is the way. So these are written. Last class we have done that. So this can be written in this continuity equation in vector form, in Cartesian form. So the momentum equations in Cartesian form, in strong conservation form. You can see one x derivative, one y derivative like that. And the energy equation, and this is the dissipation. And time marching method, last class I was telling that if I keep dou u by dou t on the left side and take all the other things right side, then this is the solution vector. And from this solution vector, I should extract the primitive variables. So if this is rho is directly obtained, so u will be rho u by rho v by rho w by rho, like that u v w I will get. And E, how to get? So rho into E plus V square by 2, V is U square plus V square plus W square by 2. From this, I can get E. And once I get E is equal to CVT, so I can get temperature. So I should be able to extract the primitive variables from the solution vector. So this is important. And this, the problem, this is time marching method. When you have unsteady flow, I march in time. Okay, this is the way. Actually, this I wanted to ask something like philosophical thing. So what is this is, if you know the initial condition in any flow domain, and I can predict what the flow will be in the next moment. If I take delta t as some 0.001 second or millisecond like that, so I can estimate what is going to be the flow after millisecond. And then using that as the initial condition, I can find out after millisecond what is that. So in that way, if I can march in time, I can find out the whole history of the flow. Am I clear?
Yes, sir.
So this is what is called as time marching. So if I know the initial condition in any flow domain, I can find out the whole history and the evolution of the flow. So it is completely Newtonian, which actually Newton says everything is predetermined. Everything is deterministic. What is going to happen in the future is deterministic. So he could, using the Newton's laws, right? I could predict when is the next solar eclipse will come, and when a comet again comes back and make a round. So the complete history of the solar system and the heavenly bodies can be pinpointedly predicted. Could they do it or not?
Yes, sir.
So what it says is the complete thing, what is going to happen is deterministic. So what is going to happen in your life also is deterministic. If I say, is it right or not?
It's not right, sir.
Then what is the what is the difference? Why you say like that?
There
This
is
is
that.
what is called as, we say, cause and effect, right? Cause and effect. Cause and effect means whatever is happening now, right? Even whatever decision you are making now is because of your past experiences. Am I right or not? Whatever is happening now, it is only because of what is happening in the nature in the previous situations. So that decides what is going to happen in the next moment.
Whatever we are doing now also will determine the next moment, sir.
Yeah, yeah. Whatever we are doing now determines the next moment. Whatever we are doing now is determined by our past.
Not completely, sir. There is something in our hands as well.
What is that?
If everything is
See,
predetermined,
now because of this meteorology and all, in Canada, I heard one of my friend was staying there, and he says whether to take an umbrella when I go out or not, how what type of dress I have to make. We decide based on the weather prediction. They pinpointedly say how the weather will be, and even after half an hour, after 1 hour, after 2 hours, exactly they will say. And sometimes, suppose you go to a automobile shop and you are purchasing a car, and we say that it is my decision. Okay, completely my decision. It is not predetermined. Can you say like that? Because many things, the decision that you have taken is because of many reasons. Maybe the many money you have, maybe the what is it, the present model, the design or something, or the forced by your wife or parents or something, or children. So all these things will make you decide only that particular model. It is not actually your decision. We feel, we deceive ourselves that it is my decision. Because I like it, I purchased. But we are forced to take only that particular one based on the circumstances. Am I clear or not?
Sir, is this like a debate between superdeterminism and free will?
Okay. Yeah, yeah. Yeah, it's a philosophical question. But if you really see like a researcher, a science student and all, a cause and effect, there is very difficult to contradict it. But unfortunately, that's what happened. Einstein, in just within 1 or 2 years, he has come with beautiful master theories, right? So what are the theories he has come with? Okay, the Nobel Prize, for what he got the Nobel Prize?
Sir,
Photo.
photoelectric.
Photoelectric effect. He came with photoelectric effect. He came with special theory of relativity. He came with general theory of relativity, which changed the complete scenario of the science. And he came with E equal to mc square, right? And so many things. And actually, his photoelectric effect is the basic fundamental uh, research for quantum mechanics. But quantum mechanics says everything is uncertain, right? That
Yes,
theory
sir.
of uncertainty. Who came with that theory of uncertainty?
Schrodinger. Schrodinger.
No, not Friedman.
Oh,
Heisenberg, Heisenberg.
Heisenberg. Heisenberg.
Heisenberg. Heisenberg. So he tells everything is probabilistic, right? Everything is uncertain. Nothing is certain. So it is completely contradicting the Newton's deterministic theory. And so actually, Einstein is not happy with that. Right? If you really believe God, we say that okay, God has determined your complete life, and it goes according to that. So believing that everything is probabilistic and uncertain, it is like disbelieving God. Okay, that's what he thought. So he says God doesn't play dice. Right? It made him very unhappy to accept the quantum mechanics. though he is one of the founder, right? Photoelectric effect is the one of the founding law for quantum mechanics. So he spent nearly after 25 years, he completed all these masterpieces in 25 years, and later the complete life, he worked to contradict his own theories, to say that quantum mechanics won't work. But unfortunately, that is right, and everything is probabilistic, and that's why nothing is completely deterministic in the nature. Okay, so many things in a macroscopic way, everything is determined, but microscopic way, nothing can be determined. There is probabilistic the thing will come into picture. Okay, that is as somebody is telling, it is philosophical in discussion. It won't end. Okay, somebody is asking something.
So Einstein wanted to believe that God is someone who doesn't play dice, right?
Yeah.
But
He doesn't believe in probabilistic thing. Okay,
but,
he says he won't play with us like that.
but if had God existed,
Yeah,
I don't want to tell if God exists or not. If had God existed,
yeah.
shouldn't he be like allowing every other possibility? Like, why should he determine everything? Why should God determine everything?
Why is he so fickle in his mind? He must have clarity about everything, right?
He just let it to the universe to exist by itself. Why should he determine everything?
Yeah,
Although he's
maybe.
aware of everything, he doesn't have to determine everything.
Yeah, maybe he has created and sitting there and enjoying whatever we are doing, leaving everything to us. Okay. So maybe, I don't know, anything can happen. Okay, leave it. Just so now this time marching method. Okay, scientifically, because we are dealing with macroscopic approach. In macroscopic approach, everything is fantastically determined, right? That's what, as I was telling, people could predict how nature behaves at situations. Only thing is, what Newtonian law says is, if you can give me, right, the present situation, everything perfectly, then I can predict the future perfectly. But only thing is, because of theory of uncertainty, we cannot predict the position and velocity of each and every particle. If I can predict it, if I can know it, then the complete future can be determined, right? So the initial conditions I have to, if I know perfectly using the Navier-Stokes equations, I can find out exactly how the nature is going to be in the future.
Sir,
Okay, nice.
sir, but in turbulence there is a time varying component. No, sir? Like whatever you said might be true for a laminar case, but when it is turbulent and things are changing with time and they're not at all, even at steady state, the one steady state achieved by one simulation need not be the same in the other simulation, right?
Yeah. So all these things, yes, that's right. All these things come with because of what is called as non-linearity. So this comes with what is called as chaos theory. And also there is another popular one called as butterfly effect. Okay. So what do you mean by linear? Linear means any change in input brings about a linear change or proportional change or linear change in output. Okay, so there is no problem. Everything behaves properly. But when nonlinear things come, uh, a minute change in input may bring unpredictably high changes in output. So this is called as chaos theory or butterfly effect. So what happens is, what is butterfly effect? Anybody heard about it?
Sir.
Yes, sir.
So if a butterfly flutters its wings here, it may become a tsunami or cyclone in New York or some other place. Okay, that is what is called as butterfly effect. There is a movie, Dashavataram. Have you seen it?
Yes, sir. Kamal Hassan Shah.
Yeah, 10 characters he has done. So at the beginning, he talks about the butterfly effect. Did you remember just one butterfly flutters its wings and some background, some dialogues will come. So it starts with something happened in ancient period, right? That is putting some statue of, some idol in a sea. Later, after many decades, it comes like a tsunami. Something like that, he says. Do you remember that? Okay, so this may be seeming to be unrealistic and it's too much like that. But I will say a beautiful example. Suppose the American president gives some statement, it may completely destroy the financial economy of one country. And Modi says something, our complete stock exchange things, no, everything will become either boom or there will be destruction. Am I right or not? A small statement by one person can change the complete scenario of the financial situation of a country. So that is what is called as non-linearity. It is like butterfly effect only. Just a statement, it completely changes the scenario and situation. Am I right?
Yes, sir.
Yeah. So this is actually all this comes because of the non-linearity in the equation. So next class we will discuss about what is non-linear equation, how to distinguish a linear and non-linear, and what is the effect of that we will see in the next class. And okay, here after time marching method, what I want to talk about is space marching. So now I have dou u by dou t plus dou e by dou x plus dou f by dou y plus dou z by dou z is equal to j. Okay, if I take steady flow, then dou u by dou t equal to 0, I have this equation. And this equation, I can write this like dou u by dou x is equal to minus dou f by dou y minus dou z by dou z plus j. Right? Am I right?
Yes, sir.
Okay, now what I do is, if it depends on the flow, all cannot be solved by space marching. And if I take a bond layer flow, right? So, or a bond layer or a flat plate. So the flow is going like this, right? If there is no separation, the flow here depends on the flow here. It will be independent of the flow on the right side, right? So the information goes in only one direction. Okay. So then what I can do is, if I know all the conditions here, I will be able to calculate the conditions at this point. Okay. So if I know at some point here, so I can just march in space so that I can find out how the flow is varying in x direction. If the flow is like this without any separations or eddies. Okay. So those only if there is no separation or eddies, then this can be written like this. E, if I, because if I plus 1, I plus 2 like that, if I have E I plus 1 jk minus E I jk by delta x is equal to minus dou f by dou y minus dou z by dou z plus j at ijk. Like this I can write. So dou f by dou y at ijk, it is something like, is equal to f I j plus 1k minus f I j minus 1k by 2 delta y. That is J if I am changing in the y direction. This is central difference like that. Okay, like dou f by dou z also can be written as f ij k plus 1 minus f ij k minus 1 by 2 delta y, like central difference like this. So I can write like this. And if I write like this, then ei plus 1 jk is equal to ei jk plus delta x into RHS at ijk. Okay, so if I know at these values at a point line like this, at I plus 1 line I can find out using this. This is what is called as space matching. Am I clear about this?
Yes, sir.
Okay, so here the thing is E is the, now which is the, what is the solution vector? E is the solution vector. So that is I am solving rho u square plus p minus tau xx, rho u v minus tau xy, rho u w minus tau xz, rho into e plus v square by 2u plus pu, and minus u tau xx minus v tau xy, w tau xz minus k dot e. All these things will be there. Okay. So from here, how to extract the primitive variables? It's very difficult. So what I do is, this is Navier-Stokes equation. I assume inviscid. If I take Euler's equation, then the solution vector will be without viscous terms. Rho u square plus p, rho uv, rho uw, rho into e plus v square by 2u plus p. Okay, these are the values I get. If I take this as C1, this as C2, this as C3, this as C4, and this as C5, how to extract primitive variables? That is, I have to express rho u, v, w, p, and t in terms of C1, C2, C3, C4, C5. Okay, so this is actually, I can show you that. Okay, this is the space matching, and these are the things I got. Okay, so how to extract the primitive variables? Actually, in the Anderson, in the exercise, the problem is given, and he has given the answer. And I want you to solve this, how to get this solution, how to get this. So this is your homework. Just you try, and we'll discuss in the next class. Is it clear?
Yes.
Actually, what is the time? We have gone beyond a lot. You don't have a next class?
At 11 o'clock, no, sir, next class.
Okay,
So
okay.
10 to 11 we have class now, sir.
Yes?
Sir, we started at 10, no? So 10 to 11 we have class. So
Okay,
it's 20
okay.
minutes left, no, sir?
Okay, okay. I thought 9 to 10. Because it is second hour, I am thinking 9 to 10. Okay, thank you. I have time. So this is what is called a space matching. Am I clear what I told? So
Yes,
this,
sir.
Yes, sir.
this is the solution vector which I am solving. So I get rho u square plus p like this, which I name it as C1, C2, C3, C4, C5. So from this, I have to extract the primitive variables, and the solution is like this: u, v, w, p, and this rho. Okay, so this you have to get the solution. Okay.
One question.
Yes.
Is there any preferred way of marching the solutions, X, Y, or Z, or does it depend on the problem?
Yeah, you cannot do space matching. So which direction I have to march, it depends on the type of flow. If I am very clear that the information is moving in only one direction this way, then I can march. But if I see something happening and if downstream is affecting the upstream, then I cannot do that. All problems cannot be solved by space matching. In time marching also, because I'm going from present to future, I can do that. If future is affecting the present, I cannot do that, right?
Yes, sir.
So
Like,
that is, if information is, this is what is called as one-way coordinate and two-way coordinate. Actually, Patankar named this. Okay, one-way coordinate means information moves in only one direction. Two-way coordinates, information may travel in any direction, right? Then I cannot use the marching. So one-way coordinate example is the time.
one
Right?
more
It's
question.
always one-way coordinate. But space coordinates, sometimes some of them can be one-way coordinate. So as I told, if information is moving in only one direction. So if you are sure about your physics, that either the information is moving in y direction or z direction or x direction in only one way, then I can use the space matching. You prescribe the conditions and a particular value of that coordinate, and then you can march. Is it
Yes.
okay?
Like if we take a supersonic wedge, like flow past a supersonic flow past a wedge, let's say it's in the
Anything, any flow, there should not be separation or eddies.
okay.
Then you can use it. Okay. Okay. This another thing. Why we need conservation form of the equations for the shock waves? Okay. So across a shock. Okay. So across a shock, there will be sudden increase in the sudden fall in the velocity, right? Mach number here greater than 1, here Mach number less than 1. So there will be a sudden drop across a micron's thickness. The shock is of micron's thickness, and there will be a sudden drop in the velocity. And pressure, there will be sudden rise in the pressure. There will be sudden rise in the density. There will be sudden rise in the temperature. Okay, and only T naught will be constant, and P naught decrease because of the entropy increase. Okay, it is irreversible. Everywhere here isentropic, everywhere here isentropic. Across the shock, there will be increase in the entropy and there will be decrease in the stagnation pressure. Okay, forget about all these things. When you study compressible flows or gas dynamics, you will come across this. But these things, there will be a sudden changes in the properties, the primitive variables. Whenever there is a sudden change or discontinuity, right? We call it as discontinuity. So whenever there is discontinuity, differential equations cannot work. Differentiation can be done only on continuous functions. Okay. Continuous functions. So I have to go for integral approach. That's why usually integral equations are called as more fundamental. It can be done for any type of variables. There can be any number of discontinuities, no problem. Integration can be done. It doesn't need any continuous function. Am I clear about it?
Yes, sir.
Okay, but I am comfortable with finite difference method, which solves differential equations. Okay, so how to go about it? So here, that's what it happens. What happens is, across a shock, so rho, there will be sudden change. So U, there will be sudden drop. P, there will be sudden rise. Temperature, there will be sudden rise, like that. Okay, so there will be like this. But if you see continuity equation for a shock, if you remember gas dynamics, rho1 u1 equal to rho2 u2. And the momentum equation, if you take P plus rho u square equal to constant, or P1 plus rho1 u1 square is equal to P2 plus rho2 u2 square. These are the governing equations, continuity and momentum equations for a shock. So if you see here, 1D conservation form of equations. Okay, so the continuity is dou of rho u by dou x equal to 0. Okay, if it is steady flow. And if I take momentum equation, dou of rho u by dou t into dou of rho u square plus p by dou x is equal to force. Okay, so I will have dou by dou x of rho u square plus p and dou by dou x of rho u as continuity and momentum equations when I have conservation form of equations. Do you remember? Rho u square plus p minus tau xx, right? So if it all these forces are assumed to be inviscid. Shock flows, if you remember in gas dynamics, it is assumed to be inviscid. So the continuity equation is this and momentum equation is this. So rho u is not discontinuous. Rho u square plus p is not discontinuous. So I can solve these differential equations when they are in conservation form. But otherwise, if I write as u dou rho by dou x plus rho dou u by dou x equal to 0, this cannot be solved because u and rho are discontinuous. Am I clear about it? Is this clear?
It's clear, sir.
Yeah. Primitive variables are discontinuous across a shock, but the products like rho u and rho u square plus p, these are continuous. And so the conservation form of equations are to be solved for shock flows. Non-conservation form cannot solve it. Either you have to go for integral form of equations and solve using finite volume method or finite element method, or if I want to use finite difference method only, then I have to solve using conservation form of equations. So there is 7th chapter in Anderson where he solves nozzle flow. We are going to discuss in the last chapter the flow through a nozzle. So there he has solved the equations using non-conservation form, and he shows that when there is a shock, it will not work. And when conservation form he used, you will get beautifully you capture the shock. Okay, so then there are two things what are called as shock fitting and shock capturing. Okay, so here shock fitting means previously in olden days when the CFD is not completely developed, and if there is a flow with a shock, right, they found it to be difficult to solve it using CFD. So what they have to do is, if I have a shock flow here, or if I have a nozzle flow and there is a shock here, so I have to know by experiments where the shock comes and solve the equations in the supersonic region. And across the shock, do you know what are the relations we use in across the shock?
Rankine-Hugoniot.
Yeah, very good. Rankine-Hugoniot relations. So if I know the values before the shock, I can use Rankine-Hugoniot relations and find out the values after the shock. And then I solve the equations in the subsonic region. Okay, why? Because the behavior of the equations are different in subsonic and supersonic flows. In supersonic flows, we call them as hyperbolic nature, hyperbolic equations. And in subsonic, they are elliptic equations. And the schemes that we use here are different, and the schemes that we use here are different. So I have to use the hyperbolic scheme in the supersonic flow, solve the variables up to the shock, and across the shock, you use shock, the Rankine-Hugoniot relations, and after the shock, you use elliptic schemes to solve it. This is the way. This is what is called as shock fitting. Knowing the shock ahead of the calculations and fitting the shock at that point. This is called as shock fitting. Okay, but you have to prior information have it, right? That is where the shock comes. So that they found it difficult. But after the time marching method, okay, what happens? This is actually steady flow. Okay, steady flow is supersonic in hyperbolic in supersonic and elliptic in subsonic. But if I take unsteady equations, I have these are parabolic in nature. Because unsteady term, I solve this using time marching. Okay, so in time marching, whether it is subsonic or supersonic, right? This behaves like these parabolic equations. It is parabolic both in subsonic and supersonic, and I can solve the equations. And by solving the equations, I can capture the shock. I can find out where the shock comes. If I give the boundary conditions and can march in time, I can find out exactly where the shock comes. So if I can locate the shock and capture the shock through numerical method, using a numerical scheme is called as shock capturing. Okay, and knowing the position of shock a priori and solving is shock fitting. Okay, previously they thought it cannot be solved like this. You cannot capture the shock. You have to get the shock through experiments, then only I can do. But now people can usually do it using numerical scheme. I could capture the shock. This is called as shock capturing. Maybe any slides are there. So this is a momentum equation and continuity equation, Y conservation form for shock waves. And see the primitive variables are jumping, but rho u is constant and rho u square plus p is constant. If you see the solution vector, I have rho u square plus p like that. So that's why conservation form of equations are good. So shock fitting versus shock capturing. So if I know the shock, this is the knowing the shock ahead, this is shock fitting. And if I can, using the numerical scheme, if I can capture the shock, this is shock capturing. And only this one small thing I will tell it. This is what is called in Patankar. Is Suhas V. Patankar, right? He is very famous. We can be proud of this. He is an Indian, right? IT Kanpur product. He worked in Imperial College London. With Brian Spalding. Right? These two people contributed a lot in CFD. Okay, these are the people to make CFD commercial. Okay, they have written the codes and made it commercial first, the CFD codes, right? So, and he has written a book in 1980. So this is the Bible-like thing for finite volume method. Numerical methods for heat transfer and fluid flow. Okay, so Patankar, he has written the finite volume method. Okay, And he has come with what is called as simple algorithm. Spalding and Patankar, they came with in 1972 simple algorithm. With Spalding he has come, and in 1980 he modified it, simple revised simpler algorithm. So he has written about this in the book. So here he has used a concept called as staggered grid. And so this became very popular and famous. And the simple algorithm, simple means semi implicit method for pressure linked equations, and this R is revised, right? So anybody working in CFD, that is finite volume method, this book is like Bible. Later, this another book I told you, Malala Sekara and Versteeg. Okay, these two people have written CFD book. This is the same book, and now this is actually the prescribed book in all IITs and many colleges, right? So CFD book. This is just like Patankar only, with some additional worked out examples, numerical examples, and all. Okay, so it became very popular. Okay, what I want to say is about the shock fitting and shock capturing. Initially, people used to solve it using shock fitting approach, knowing the shock position ahead of the calculations. So solving hyperbolic equations in supersonic flow and using Rankine-Goniet relations, and then solving the elliptic equations in subsonic flow, they used to solve the whole thing. But now using time marching method and taking unsteady equations, which are parabolic, and they used to capture the shock. Okay, so that's what they are doing. Okay, so now Patankar came with these generalized equations, the transport equations. He has told expressed in a different form. Again, this is unsteady term, then this is convection term, and this is diffusion term, and this is the source term. So he has written all the equations in a particular format. Dou of rho phi by dou t plus del dot rho v phi is equal to del dot gamma del phi plus s phi. Okay, so all equations are presented like this. If phi equal to 1, this becomes continuity equation. And phi equal to 1 and gamma equal to 0, s phi equal to 0, I get the continuity equation. If phi equal to velocity and gamma equal to mu and s phi is equal to minus del p plus rho b. Okay, so this becomes a momentum equation. Am I right? And energy equation, phi is equal to E plus V square by 2, and gamma equal to K, and S phi, it will have all K del square T plus rho B dot V plus rho Q dot, right? All these become source terms. And this is unsteady term. This is convection term. This is diffusion term. This is source term. So the convection term is in divergence form. Okay, this is the way I can write all the equations in a single thing. Okay, so this is called as general transport equation. And so in finite volume method, what they do is this generalized general transport equation, which is differential equation, this is integrated, integral of all those things. Okay, so this is the way the finite volume methods are solved. Okay, that is about this. Actually, I stop here. Okay, exactly time. Any questions? Okay, with this, I complete governing equations, right? So mainly you go through Anderson book, the complete second chapter, and okay, some things here and there, some additional things may be there. There are some other books, so you can go through the notes like enthalpy equation and all. So next class we will deal with behavior of the partial differential equations, because all are partial differential equations. We like to know, I was telling elliptic, hyperbolic, parabolic, all those things, and how to know that this is this type of equation like that. Those things we will discuss in the next class. So if there are no questions, we will go for the story. Anything? Okay, people are there, right?
Yes, sir.
Okay.
Yes, sir.
Because unless you respond, I will not know. Okay, it's a small story. The emperor and a beggar. In the dusty streets of a large city lived a beggar procuring alms and rice daily from passers-by. Most of the days he was unable to gain enough food for a meal and enough coppers to buy some firewood to cook and keep him warm. At night he slept under the sky with only a rag to cover him. His life was difficult, but he had grown used it over the many years. One day the beggar heard the news that the emperor was coming to town for a rare visit. I am sure the generous emperor will see the state I am in and grant a generous gift. The richest of all men will bestow some sympathy and relief on me in a manner that would undoubtedly surpass the paltry givings of the regular citizens, he thought. So he made plans to seat himself along the route the emperor will be traveling, so that the emperor do not miss to notice the beggar's misery. He gathered all his belongings and set his spot on the street before the night before the procession. And the royal caravan finally approached and stopped right in front of him around the midday. While the beggar had expected no more than a little gift to support his life on the streets from the emperor's servants, he was speechless when the cavalcade halted beside him and the great ruler himself emerged in front of him. The emperor approached the beggar, shook the poor man's hand, touched him gently on the shoulder, and looked into his eyes and said, "Tell me, kind sir, may I have a little gift of rice?" The emperor asked the beggar, "Tell me, kind sir, may I have little gift of rice?" For a moment, the big beggar didn't understand what the emperor had just said. The emperor motioned to his bowl with some rice, urging him on, "Can you please spare some grains of rice?" The powerful man insisted. The beggar could barely believe what was happening to him. He was expecting the great emperor to ask him anything. He wasn't expecting. He had only a handful of grains to his name, but he was being beseeched by he who had everything. The beggar slowly took the bowl into his hands and started and stared at the little rice he had. He has only little rice is there, and the emperor is asking rice, and he knew he could not deny the emperor's request by any means. He was barely able to hide his indignation, but he reluctantly counted 5 grains of rice and dropped them into the hands of the emperor. And the emperor thanked him and shook his hand once more and went on his way. Confused, hurt, and angry, the beggar watched the caravan disappear into the dust and left him alone with nothing more than he had before. That night, while he was cleaning his rice for his dinner, he noticed something glinting in his bowl. He looked closer and a thrill shot through him. Then he put the tiny gold nugget out of his bowl. Okay, so a gold coin like thing he found. The gold nugget was enough for him to buy him a few months of the street. So he can have for a few months good food. There must be more of it, he thought, and started to go through the rice in search of more gold. He found 4 more pieces of gold nuggets inside his rice bowl. As he stared down at the small fortune in his bowl, it dawned on him. Then he thought there were 5 gold nuggets, one for each grain of rice he had offered to the emperor. Okay, so he has begun because he has given rice pieces, he got 5 gold nuggets, right? So then he understood, okay, what we give, what we get depends on what we give. Only by giving, you are able to receive more than you already have. Okay, thank you. Thank you very much.
The beggar gave linearly, and like the king gave linearly. It's not linear.
Yeah. Yeah, it's a linear relation only. But highly steep.
Yes, sir. Right. Constant is very high.
Yeah, yeah. Yeah. Okay, thank you. See you again. I'll stop this.